Okay, so at the end of the last class, we were talking about DC bias point and amplifier operation. So we were able to combine both a small signal and a large signal source at the input gate of the MOSFET, and see how the MOSFET can be operated as an amplifier for the small signal. And we saw what the limit is on the small signal, and that was related to where you placed your operating point, which, in this case is plotted on the ID versus VDS plot here. So as we said in class, ideally we would like to operate this for a given value of gate voltage. We would like to locate this Q, or the DC operating point, as far away as possible from the triode region, saturation triode region border, as well as far away as possible from the cutoff point. So this is called a load line. This load line is calculated, we did the calculation analytically before, and graphically you can find this operating point by solving the initial equation that we had, which was what? If we look at our circuit looked like this. This is S, this is my drain, this is VDD, this was RD, and this was my gate to source voltage. So we said that VDS, which is the voltage of my output here, is equal to VDD minus RD times ID. And if I solve for ID, I get what? If I solve for ID, I get, I will divide by RD, this goes away, and then I bring ID on the other side, and I end up with this equation here. In this equation, I can substitute with VDS equal to 0, and I will get a certain value of ID. So if I substitute with VDS equal to 0, then I get this point here. I get a certain value of current. This is 0. I get certain value of current equal to VDD over RD, and that is the value of current here. And I can, on the other end, I can substitute with what? For me to find this point, I would like to substitute with VDS equal to VDD, since we know that's the maximum value of drain to source voltage that we can have, right? This is my drain to source voltage. If there's no drop across this resistance, then the value of VDS is equal to VDD, my supply voltage. Yeah. So if I substitute with VS equals VDD, this is VDD over RD, and I end up with current equal to 0. And that's what I have on this end. So I have this point now, and I have this point now. Depending on what value of gate voltage I'm applying, I will be on one of these curves. So let's say I'm applying this value VGS, then I'm on this curve here, and this load line, which has a slope of -1 over RD, intersects the characteristics, the ID versus VDS characteristic of the diode at the DC operating point. So again, that's just an explanation, further, better, maybe a different graphical explanation of the DC operating point versus the analytical method we followed in the last class. So now, again, in the last class, what we did was we assumed we have a small signal and a large signal together. What if we only have a small signal, or if we only have a large signal? We assumed we have them together, and we solved the problem with both of them together in the circuit. Yeah. But we know that, again, if I'm operating in saturation mode, I'm operating on a voltage transfer characteristic, meaning my relationship between VDS and VGS is governed by this relationship. And if I'm applying a small signal, then I'm at around an operating point, and I'm operating on in a linear mode. So I'm operating this device in a linear fashion. So if this device is operating in a linear fashion, meaning this device looks like a linear circuit for my input, then theoretically I can apply superposition and maybe look at the effect of VGS by itself, and look at the effect of small VGS, so the small signal by itself, and then the DC operating point or the DC bias point by itself. So in the last example, we did not do that. In the last example, we considered them both together. And we plotted, we looked at the voltage transfer characteristic, the corresponding voltage transfer characteristic. But now, what we will do in this next section is try to see what happens if we can we split them? You know, is this, since we know this device is linear, how do we split this these two sources and operate and apply superposition to simplify how we analyze circuits and to build more complicated circuits towards the end of the chapter? So, to that effect, okay, we revisit the idea of small signal operation and models. So the idea is to come up with a model, a separate model that allows us to do small signal operation by itself. So in order to do that, we have to derive a set of equations that clearly demonstrate that we can utilize superposition. So in order to do that, so let's start at what we know about DC operating point. We know that if we are not applying a small signal, my DC current, ID, my DC drain current is governed by the equation that governs current, which is controlled by the gate to source voltage. This is the equation that governs the drain current in saturation mode. So this is applicable only in saturation mode. So I have to make sure I'm putting the device in saturation mode, meaning the drain to source voltage in saturation mode is greater than the overdrive voltage. So I have to make sure that VDS is greater than the overdrive voltage. If I do that, then I'm in saturation mode. If I'm in saturation mode, I can use this equation for current. For assuming I don't have a small signal input. If I have a small signal input, then I have to take that into consideration. And then what did we do to confirm or understand the DC operating point more? Fine, we said that we will take our output between the drain and the ground, because since it's a reference to the source, and we'll add a resistor here to be able to basically control the value of my VDS voltage somehow, since this resistor is now multiplied by the current, which I have control over. And again, we have ensured that the drain to source voltage is greater than the overdrive voltage, so I'm pushing this device to operate in the linear region. Now that I'm in the linear region, okay, I've now put in a small signal in addition to my large signal. How do I deal with that? We dealt with that in the previous analysis. We dealt with that in the previous case. We dealt with both signals together. So now we would like to see if I can deal with them independently. So if I put the small signal, then the total gate to source voltage, so they use a small v. So for the DC operating point voltage, or for the large signal voltage, they use capital G, V, capital G, capital S. For the small signal, they use small v, small g, small s. For the total signal, they use a small v, capital G, capital S. So my small v, capital G, capital S, that's the total voltage between the gate and the source. That's equal to my large signal, or my DC operating point voltage, the gate voltage, and my small signal that I'm adding. So if I am pushing this device into saturation, we said we can utilize the equation for current that is given in the previous page, which is half Kn VGS, again the total VGS in this case. So total VGS would be the DC operating point voltage plus the small signal voltage minus Vt. So that is the current, the drain current, considering both sources, right? And then I have to subtract the threshold voltage and square. If I expand this, I get three terms. So the first term here is what we saw on the previous page, which was the effect of the large signal analysis, or the large signal source, on the drain current. It was only equal to half Kn capital VGS minus Vt squared. That is the effect of the large signal source, capital V, capital G, capital S on the drain current. How about these other terms? So this is term 1, this is term 2, and this is term 3. So term 1 we're okay with. Term 2 is the effect of the small signal on the drain current, ID, at a specific value of capital VGS, which means this is my small signal analysis, the small signal effect, right? So I'm operating at a specific gate to source voltage, and I'm applying a small signal. So this includes a linear relationship. So this includes a linear relationship between between gate to source voltage and my current ID that is due to that additional small signal voltage. This third term is a distortion. It's a nonlinear term. It's a square term that we will not. I mean, it's taking the small signal and squaring it, and then that is what is proportional to the output current in this case. So this is what's going to control the limit of my small signal VGS. So if my small signal VGS is small, so if I have a if 0.1 squared is 0.01, so it becomes smaller. So if my VGS is small, so we'll find out what small means. If my VGS small signal is small, then this third term can vanish, and I'm left with only the second term here having any significant effect on the current ID, right? So this is going to limit, this third term is what's going to limit the magnitude of my input signal that I can amplify, push into the amplifier or amplify. Okay, so what is the limit? The limit is we would like to make sure that, according to this equation, I would like to make sure that this half Kn times VGS squared is smaller, significantly smaller than this term here, right? So let me solve the inequality. This inequality is solved in the next page, and then we will find the limit on VGS, right? If we look at this inequality, and solve for VGS by itself, we will see that VGS should be significantly smaller than twice the overvoltage that we're applying. That is the limit in order for us to be able to have ID here, this ID equation, composed of only the first two terms. The third term will be insignificant in that case. So if that's the case, that means that my total drain current is now approximately a summation of the effect of my large signal by itself and the effect of my small signal by itself, which means that the current due to my small signal is equal to that second term only. It will not include this third term. It will only be the effect of this second term into the picture here. So now my small signal current is equal to this, and this is a relationship between, again, similar to what we've been doing before, this is a relationship between a current and a voltage. That's the linear relation between current and voltage. Linear relation between current and voltage are governed by, are can be modeled as a resistance. In this case, since it's I here and V on this side, so V equals IR, so V multiplied by 1 over R is equal to I. So again, this becomes like a conductance. So this is it's called the MOSFET transconductance. And it's basically my current gain, the current gain between my gate to source voltage and my drain current. So I will put in a certain gate to source voltage, small signal, multiply that by my gain, and then I will get my corresponding small signal current. This is above and beyond my operating point. So it's not equal to my operating point, it's beyond my operating point. So that's MOSFET transconductance variable is GM. GM is equal to this constant here. So that is what GM is equal to. And then the VGS minus VT is my overdrive voltage. So that is my GM. Again, we can also look at this a bit more graphically. And if since we have a relationship between ID and this ID, the full drain current, and we have the relationship between the full drain current and the full gate voltage, which is this equation up here. I can take, at this, I can plot this equation the relationship between the drain current and the gate to source voltage. So I can plot this equation, and at some point in this plot I have my DC operating point, and this DC operating point, around that DC operating point, the slope at the tangent at the DC operating point has a slope that is equal to my transconductance here. So it's the differentiation of the total current with respect to the gate to source voltage here, the total gate to source voltage. Okay, so small VGS is my total gate to source voltage, which means I have to go back to this equation here, since this equation here is what takes into account the total gate to source voltage. So I plot this equation for various values of VGS. So I'm given VT for a specific device. I have Kn for the device. I will plot for a specific DC operating point. I will have that. I will know what that is. I will plot for various values of the gate to source voltage in this equation, knowing the two components of the gate to source voltage, the DC operating point component and the AC component. I can plot that curve, and the tangent to that curve is also the transconductance. The other way to so if you don't want to do it graphically, analytically, it's equal to Kn times VGS minus VT. So the transconductance, the gain, will depend obviously on the DC operating point. And we saw that before, right? We saw that the gain will depend on the DC operating point that you're operating at. We saw that before when we calculated the gain as AV for the total signal, the DC operating point plus the small signal analysis. Okay, so now this is what? This is a current gain. This GM is a current gain from small VGS to ID. Using the same logic we followed before, since it's a current gain, and this is a current gain controlled by a fixed variable, a current gain controlled by VGS, then the small signal model, like the large signal model, looks like what? Looks like a voltage controlled current source as well. Like my large signal model looked like a voltage controlled current source. And here I also have a voltage controlled current source between my drain and source, and that is equal to small ID. Before that was equal to, if you were talking about DC operating point only, then this was my ID current, which was in saturation equal to half Kn VOV squared, right? And then we included the small signal effect with this in the last example, and now we are splitting them together. So we are not including ID plus ID together as one equation for current like we did in the last example. Here we are splitting the small signal by itself. So the small signal will also by itself look like a voltage controlled, meaning controlled by the gate to source voltage, a voltage controlled current source. So I still have a model like this. Again, like we did before, it's convenient to just use, since my circuit already contained this RD, then it's convenient to take your output voltage between drain and source as such. So this will be your VDS output due to your small signal. So it's not due to your gate to source. So this is your small signal voltage at the input is causing this ID according to this equation. And the output is VDS, small signal VDS, that is taken across these terminals. But we have to note something, that we have two effects that we need to consider here. We said we can apply superposition since this is a linear circuit here. So two things we have to consider. At the input we had VGS small signal and VGS capital. So now my input voltage is only, since I'm applying superposition, I will have to short one source that I'm not utilizing for the calculation. So I will short this source. So I'm left with only small signal VGS, and that's why I put small signal VGS here at the input of the amplifier model. And then I create my ID according to this equation, and at the output I create a VDS. But there are two things at the output that have to be taken into consideration. When you're applying superposition, all sources that are not used to calculate a specific output voltage need to be shorted, right? You need to look at the effect of every source at a time. So we need to also, this was my MOSFET, this was my ground, this was my resistor RD, this was VDD before, that was used to calculate your DC operating point. This is a source, VDC, this is like having a battery here, right? This DC operating point had an effect on the DC operating point that you've calculated here using this current. But now I'm no longer calculating the DC operating point, I'm only looking at the AC operating point. The only thing that affects the AC operating point is this VGS according to our equation here. So this actually also has to be a short circuit, which means that this resistor now needs to be placed at the output. So this resistor is not here, not up here anymore, it's down here. So current that's flowing will be flowing through this resistor and hence creating an output voltage VDS. The other thing that we need to consider as well is if we're going to include the effective channel length modulation. We said that the effective channel length modulation is that the output current will increase. This is the effective channel length modulation. Ideally, without the effective channel length modulation, this is ID versus VGS, so versus VDS. Sorry. If I'm going to include the effective channel length modulation, then this is not straight. This is on a slope like that, and the effect is that I have to put an output resistance. So this is no longer an ideal current source with an infinite output resistance. It has an R output here as well. Right, so now this becomes my small signal model, and see the effect of adding this output resistance is a reduction in the output voltage. Since the parallel combination will be smaller than both of them, then I've reduced, it's the same current that's flowing, but I've reduced the resistance by putting the resistors in parallel, so I've reduced my output voltage. That's the effect of this channel length modulation here. So that's something to consider. So now I've concluded that I have a current gain of some sort, and now this section talks about the voltage gain. So basically putting the resistor that we were talking about in parallel. So placing the resistor in parallel means that the gain, or the voltage at the output, is equal to minus GM times RDI. I think I just plotted that and I explained it, but I'll redraw it again. So what these equations refer to is that the output voltage now versus the input voltage. So my input voltage is VGS, so my small signal input voltage is plus minus VGS. This creates a current small signal ID. This small signal ID has a value that is controlled by the gain. If you go back to what we have here, so ID is equal to GM times VGS. ID is equal to GM times VGS, right here. So I will, instead of putting ID, I will put GM times VGS in the equivalent circuit. So I have an equivalent circuit that looks like this. Again, input small VGS. This is your current source equals to GM times VGS, and I have an output voltage VDS, small signal. I have a resistor here, RD. I will not include R output for now, I didn't discuss that yet in these equations yet. So note one thing, that since the current is flowing in this direction, then the voltage is in opposite polarity to the assumed VDS. That's why there's a negative sign here for the voltage gain. So the relationship between VGS at the input and VDS at the output is related by GM, the gain that we have, times RD. Okay. Okay. That being said, we will on the next page. I think they draw the equivalent circuits. So now I have a voltage gain. So again, the flow is as follows. We first proved that we can. We have an equation with three terms, and we first proved that if this term is very small, I can apply superposition and look at this term by its own, which is the DC operating point, and this term by its own, which is the small signal effect. We said that we looked at this a little bit more closely on this page, and we concluded that the relationship between ID small signal and VGS small signal is this transconductance GM. This is the gain between a certain gate to source voltage and my output current. I would like to create an output voltage. So what did I do? Since I'm applying superposition, we said that RD will have to be placed in parallel with the output. So, and this is the effect of that. This is the effect of placing RD in parallel with the output, which means if I redraw this, I think let me just move forward. This is the effect of placing RD parallel with the output. So here, let me rewrite this as follows. So this is VDS, so this is my VDD, this is RD, and this is my output VDS. So VDS is equal to VDD minus RD times ID. Under the small signal condition, we have instead of this ID here, which is the total current, is equal to the DC operating point current plus the DC operating point current, capital letters, plus the small signal current. So, which means that my total VDS is equal to my VDS due to my DC operating point minus RD times ID. So if I'm going to, since we said that superposition can apply, then VDS due to only my small signal is this component here, which means that VDS due to my small signal is equal to minus ID times ID. We said ID is equal to GM times VGS from the previous slide, which means this is equal to VDS. So if this is equal to VDS, this model means that the resistance, basically, RD has to be placed in parallel with the output here, and I have to have this current that is equal to GM times VGS flowing through it. That's basically what this means. And now that we've established that, again, this only worked. Again, all of this worked only when I made sure that VGS is much smaller than 2 times the overdrive voltage. That's something I stressed again after we discussed here. So separating DC analysis, we said that this only works if my signal, a small signal, is significantly less than the overdrive voltage. They said that's half the signal, or the signal, or the signal is less than the overdrive voltage, significantly less than the overdrive voltage. So the model that we have been talking about is called the small signal equivalent circuit model, or the small signal model, and this is this model that we have been discussing. As we said, this model this model does not include this the effect of RD yet, but they put in R output. R output was the effect of the finite channel length. So that was modeled as an output resistance here. And then, next they will include RD there and talk about why they included RD. And we said that, R output is a large value, so fine, since it's a large value, it will, you have current flowing through it and you have a large voltage gain. But since it's in parallel also with another, it was infinity before. We initially assumed it was infinity, so we even had a higher voltage gain. So, fine. So the effect of our output is a reduction in the output voltage. Our output, we said from before, it's the same output we had before, is due to the effect of the early voltage. And this is how we would calculate. Our output, typical value for our output is between 10 to 1000 kilo ohms. So as you see, it's considerably large. And again, this is what I was talking about in the idea of RD coming in parallel with our output. Because we were assuming that the device is linear, now I have to, in parallel with our output, bring down my RD. RD has to be brought in parallel since this is using superposition. For instance, I'm utilizing superposition. I'm only utilizing small VGS. Capital VGS was grounded. This source is grounded. RD was here, and I had VDD here. VDD also has to be grounded. Right? So now my output voltage, which is this point, between this point and ground, which is small signal output voltage, sees this resistor in parallel with our output resistor due to the early voltage, and then this current is flowing through the combination. So the effect of this resistor, our output, is a reduction in total output voltage, capital or small v ds here. Okay, and that's what this equation says here, right? So that my gain now, instead of being equal to only GM times my output voltage. So if I supply a certain gate voltage, I would like to get a certain output voltage. The relationship between them is governed by my gain. Before, I was basically taking my gate voltage, multiplying it by GM. That was my current gain due to the small signal originally, when I was not considering the effect of this RD or R output. This was the current gain. And then I wanted a voltage gain. For me to get the voltage gain, I considered RD. But when I considered the effect of early voltage, I also considered the effect of R output. So hence I have these two resistors in parallel controlling my output voltage, or the voltage gain of the device. So more on this transconductance. So this transconductance can be, again, it's obviously a device characteristic, but and that's what this section is talking about. So this transconductance parameter for the MOSFET, GM, can be, you can solve it if you look at the equation 5.47. So let's go back to equation 5.47. The 5.47 says that GM is equal to Kn VGS minus VT. Kn is the transconductance parameter. We can expand that into Kn prime, times W over L multiplied by this. That's equal to GM. So that's what they did here in this section. So Kn prime W over L times VGS minus VT. So what they're doing in this section is they're deriving three different equations for GM, and they're all from each other. So this is one equation for GM, and this is one equation for GM. It's another equation for GM, and we have a third equation from GM at the bottom here. Each one of these tells us something physical about the device. So it just says that here I would like to increase gain. For me to increase gain, I need to do what? I need to increase the width of the device and maybe decrease its length, or basically increase this ratio. Another way I can do it is to increase the overdrive voltage. If you increase the overdrive voltage, remember what happens. Overdrive voltage was the limit here between your saturation and triode mode. If you increase the overdrive voltage, and this was the overdrive VDS here was equal to the overdrive voltage. That was the limit here. If you increase the overdrive voltage, that means I'm pushing this further up. If I push this further up, I reduce the range of operation as an amplifier. Right? If I push this further up, I will push this triode region to the left. Right? I reduced my ability to operate as an amplifier. Fine. So I reduced my ability to operate as an amplifier to locate my operating point, which means my operating point is limited to a small space. If my operating point is limited to a small space, then also my signal swing is limited to a small space as well, right? So fine, this is a way to do it, but you will be limiting, for example, signal swing, and you will have to live with a wider device, which may be okay. What this says is that the gain is also controlled by your DC operating characteristics. So here we have gain controlled by dimensions and overdrive voltage. Here we have gain controlled by dimensions and DC operating point. Here we have the third equation for gain that they have. We have gain controlled by overdrive voltage and DC operating point. Right? So which means I have what? I have dimensions of the device and the overdrive voltage and the DC operating point. These are three parameters that control my gain. The gain can be controlled by either two of them. So if I choose two, I get a third one. I mean, I don't have a choice. The third one I have to comply, because this is gain and it's controlled only by two of these parameters. This is gain is controlled by two of these parameters. This is gain and it's controlled by two of these parameters, which means the third is defined. Right? So this is just talking about the effect of device design on the gain. So basically, what the conclusion of this page is the fact that the MOSFET gain GM depends on device size. At the end of the day, we are gonna have to make sure that we have a certain size if we want to have a certain gain for the MOSFET. So we will find that this is not the case for the BJT. It's not going to merely depend on size for the BJT device, which we will study next week. So that being said, there are a set of examples here that Wissam will go over with you in the recitation session. I would like to talk about one last thing. So we talked about this model. We derived this model. We figured out how to come up with this. So this is my small signal. Again, this is only for the small signal. Only small signal. I finished. My DC operating point is done. I know where my DC operating point is. If I have a specific DC operating point in mind, then I go to ID is equal to half Kn V of V squared, and that's it. I know what my ID is, and I know what my VGS is, capital VGS. That's it. It's done. Now, since I'm using superposition, I can start building useful things with models for the small signal equivalent circuit. So this is the model that we derived for the small signal equivalent circuit. This is called the pi equivalent model, or pi equivalent model. We will come up with what is called a T equivalent circuit model. It's something that will help us solve circuits more easily. So we will transition from each of these models, and we'll see that they're all equivalent. So the idea is to come up with an equivalent model for this to this pi equivalent model, so we can solve circuits easily. So here, what did I do? I kept my input the same, and I added a current source here. This current source has the same value. So since it's the same value, I'm not changing anything. So no changes happen, so I can go to this. This is equivalent to this, no problem. Now let's see what we did here. What we did here is brought this node to this point here. If I bring this node to this point, and I'm saying that this gate current is equal to 0. When I solve my circuits, I know that this Ig is equal to 0. What does this mean? It means that there's no change to the circuit. This current is flowing this way and then it's flowing this way out to the source. So this circuit is equivalent to this circuit. The other thing we can do is, okay, I can keep this terminal as it is, bring this terminal to the top like that, and then put my source terminal here. What do I know about what's happening at VGS? So I know that the voltage between this node is VGS, and we know that this current is ID. ID is GM times VGS. So GM times VGS is the current that's flowing here. If I put a resistor equal to 1 over GM, then this voltage across the resistor is VGS. So these two circuits are equivalent. And this is called a T equivalent circuit. So this is like a T on its side. And it's called the T equivalent circuit model for a small signal equivalent. T equivalent small signal circuitry. So this will help us solve some problems in this section. Here I take my T equivalent circuit model and I include the effect of channel length modulation, which is our output. So I include the effect of our output here. These two are equivalent. They just, instead of writing GM times VGS, we write I here. So there is nothing changing here. But this R output is the effect of the channel length modulation into this equivalent circuit. And the rest are examples. So Sam will be solving these examples with you in the recitation. And this, like we did for the large signal analysis of the device, this is sort of a summary of everything we've discussed. So this is called the hybrid pi model or the pi model. And this is the T model equivalent circuit for small signals. So, and these are the main equations for utilizing those. And we will stop here. We will stop at the end of section 5.5. So we will not be doing section 5.6, and I will be modifying the homework problems to reflect that. I may cancel some problems to reflect that.